Hello, I'm an AI architect based in South Korea, and over the last few days, I have been able to stop thinking about a flurry of new ideas. They've been constantly flowing out like a fountain, even waking me up in the middle of the night to reorganize them. So I decided to record this video, and please note that this is an early stage idea rather than a finalized theory. So I will deleting all negative comments. If you have time to leave, hey, you should spend that time working as hard as I do. I only got 2 hours of sleep last night. Yeah. Now that I've covered the background, let's start. I'm gonna shift gears now. Just imagine an underlying reality to details for any observer fully perceive. Like infinite state, infinite information, continuous change. And somehow observers can constantly induce stable representations. And that's alright the question. Why does observation create stability? And honestly, everything I'm about to talk about began from this question. My answer is that stability not in reality but in representation. Think about it. Any observer fundamentally limited. No observer possesses infinite memory, infinite precision, or infinite temporal access to reality. Therefore, every observer must compress reality. Within an observer model, M represents the underlying continuous reality because observer cannot process this infinite information. They apply a compression map P, and this induces a finite representation space S. Then S is the induced representation of M under P. To understand how this compression actually works, we need to realize one thing. The observer never directly accesses the underlying reality at the microscopic level. Instead, it only perceives equivalence classes induced by indistinguishability under finite observation. The underlying reality consists of infinitely many microscopic states that differ at arbitrary fine scale. However, the observer has finite resolution. Many distinct microscopic states become indistinguishable. In other words, different microscopic states may be mapped to the same representation, inducing an equivalence relation over the underlying state space. What the observer actually perceives is not the microscopic itself, but the compression representation structure induced over it. What happens if every observer is constrained in only three ways? The first constraint is finite resolution. It means no observers can store infinite detail. Representation must be finite. And the second constraint is bounded sensitivity. Under a Lipschitz constraint, small perturbation in the input should not completely destroy the internal representation. If the mxy less than 1, then the sfx fy less than 1. So to rephrase this, nearby inputs should map to nearby representations. And the last constraint is finite memory. Since an observer cannot retain an infinite amount of fast information and is restricted to finite memory, notion of causality and Markov sufficiency naturally emerge. In other words, once memory is fundamentally limited, the system is forced to approximate the present using only a bounded portion of the past, which induces an effectively causal and Markovian structure. I'd like to add a little more mathematical intuition to the second constraint. First, we introduce a Lipschitz constraint. Mathematically, it can be written like this. In our framework, M represents the input space, F is a representation mapping. The M and the S are distance metric defined on the input space and representation space respectively. L is the Lipschitz constant and S denotes the representation space. What this equation essentially means is that under the Lipschitz constraint, if the input change only slightly, then the corresponding change in the internal representation should also remain small. In other words, states that are extremely close in the input space, such as x and x plus epsilon, should not suddenly explode into completely unrelated vector once mapped into the representation space. For example, in a deep learning model, adding a tiny amount of noise to an image of a cat should not cause the internal representation to abruptly shift into something semantically unrelated like a car or a lock. The core idea is that local permutation in the input should preserve local structure in representation space. And also, different observers may vary in quality, but stronger observers maintain representation stability instead of letting small input change alter meaning discontinuously. From an observer perspective, stability and order allows how information is filtered and compressed under finite observation constraints. The underlying reality M can be thought of as a high-dimensional continuous space containing complex microscopic fluctuations. This low structure is not directly accessible to the observer due to limitation in resolution, sensitivity, and memory. As a result, the observer applies a completion mapping that transforms M into a lower dimensional representation space S. Under the three constraints mentioned earlier, an important phenomenon occurs. Not all microscopic distinctions are preserved under the mapping. Instead, only those structures that remain stable under perturbation and repeated compression persist in the representation space. This persistent structure emerges as stable regions within us. These stable regions correspond to representations that remain invariant under noise, perturbation, and partial observability. In this sense, stable reality is not a property of input space M itself, but of the invariant structure induced in the representation space by the observer's constraints. So under this observer's constraints, stable region emerges within the representation space S. The next question is, what property must a representation have in order to persist under this constraint? In my framework, three fundamental invariants begin to emerge. This is not additional assumption, but property that are preserved by the representation process itself under finite observation. The first invariant is stability. Stable representation are robust to small perturbation and preserve their identity under local change in the input. The second invariant is persistence. Some representations remain invariant across time, maintaining their identity under temporal evolution of the underlying process. The third invariant is Markov sufficiency. Because observers have finite memory, any representation of present must be conditioned only on a bounded history, inducing an effectively Markovian structure. In other words, these three invariants define the class of representation that remain well defined under finite observation. So after introducing the observer's constraint and the invariant structure that survive them, one can now ask what all of this ultimately implies. Stable representation may emerge not because the underlying reality is intrinsically stable, but because a finite observer can preserve only certain invariant structure under compression and limited observation. In other words, stable reality can be understood as an emergent property of finite observation and representation invariance. From this perspective, what is referred to as reality is not the underlying system itself, but the structure induced within the observer's representation space under this constraint. And we can compare existing frameworks. My framework starts from a more primitive set of assumptions than existing approach. The central question is what's supposed by finite observation itself. The goal is more fundamental to identify which persistent invariants necessarily emerge when a continuous reality is accessed through finite observational constraints. Coarse graining already assumes a partition scale, but where is that scale specified? Information bottleneck assumes a target variable y, but what defines relevance in the first place? Markov model begin with transition kernel, but these transitions are typically assumed rather than derived. In essence, existing framework asymptotically assume a representation structure, whereas my approach derives from observer limitations. Instead of assuming states, kernels, or objective, I begin with the following constraints which determine what's effectively observable within the system: continuous underlying dynamics, finite observational capacity, persistent constraints. From this limited observational regime, discrete stable structure emerges as invariant in the representation space. So the central claim is that stable reality may emerge as a consequence of representational constraints. An observer cannot access the full underlying reality M. Instead of it only observes a subset of information and maps it into a complex representation space S, which serves as its internal model of the world. Once this mapping is fixed, all subsequent inference about M is performed entirely within S. In this sense, S functions as a self-contained representation system. From this perspective, what is referred to as reality corresponds to a system induced by finite observational constraint. I will next reframe it in a machine learning setting and formalize it. Thank you for listening.